In this video, we are going to find the Laplace transform of these trig functions, sine of at and cosine of at. So if you watch my previous video, I derived the Laplace transform of 1 e to the at and t raised to the power n. Here in this video, we are going to do the trig functions. So let's recall the definition of the Laplace transform of the function. So the Laplace transform of a function f of t, just to refresh your memory, this is the integral from 0 to infinity of e raised to the power negative st, and this is multiplied by the function f of t dt. Right, we know this, and now we are now going to find the Laplace transform of the function. So the Laplace transform of the function sine of at and cosine of at. So the Laplace transform of the function sine of at, this is equal to what exactly? So that is equal to the integral from 0 to infinity of e raised to the power negative st, and this is multiplied by the function sine of at and then dt. All right, cool stuff. So here what we can do is to apply the integration by parts. So this is what I'm going to do for the integration by parts. So let me switch colors here and then we deal with that. So integration by parts, di, d for differentiation and I for integration. I am going to differentiate the sine of at, and I'm going to integrate the e raised to the power negative st. This is plus, next one is negative. Differentiating sine of at is going to be a times the cosine of at. This is using the chain rule, and now integrating this one, that is going to be negative 1 over s e raised to the power negative st. Alright, cool. So now integration by parts, we multiply diagonal terms. We are done with the integration, but when we multiply terms horizontally, we have to take the integral. So now integration by parts, let me write this one as the Laplace transform of the function sine of at. Alright, so this is equal to, now applying integration by parts, that is going to be multiplying diagonal terms, that is going to be negative sine of at. This is multiplied by e raised to the power st, negative st, divided by s. You are done, you put the limits of integration from 0 to infinity. And now negative, negative, when you multiply, that becomes positive. So plus the integral from 0 to infinity, multiplying them, that is going to be a times cosine of at. And this is multiplied by e raised to the power negative st dt. This is divided by s at the denominator. And we close that with a square bracket. Cool. Now, when we plug in the limits, the Laplace transform of the function sine of at, this is equal to what really? So the limits, so we are taking the limits as so negative. We are going to take the limit as t approaches infinity of sine of at. This is multiplied by e raised to the power negative st all over s, right? So s here is like a constant. So when we do this, then we subtract the lower limit. The lower limit, when you plug in 0, sine of 0 is going to be 0 and e raised to the power 0 is 1. So the lower limit evaluates to 0. Then we have plus the integral from 0 to infinity. A over s is a constant in this case, so I'm just going to factorize a over s out, and that is going to be the integral from 0 to infinity of cosine of at, and this is multiplied by e raised to the power negative st and then dt. Cool. So as t is approaching infinity, this one is going to be approaching 0 because the numerator is going to be approaching negative infinity. So this is going to be approaching 0, which is multiplied by this. Everything is going to be 0. So this one is going to be 0 as t is approaching infinity. So the Laplace transform of the function sine of at, this is equal to, everything here is going to be 0, and what is left is this. So this one is, the negative is multiplying up to this point, and then I'll have to clean this. I'm sorry about that. Okay, so what is left now is this. So we are now going to have a over s left, and this is the integral from 0 to infinity of e raised to the power negative st, and this is multiplied by the cosine of at and then dt. Cool, right? So now how best can we write this? So let me switch colors and then we'll write it here plainly. So this Laplace transform of the sine of at, so the Laplace transform of the function sine of at is equals to a over s. But looking at the definition of the Laplace transform, this one too is the Laplace transform of the cosine of at. So if we go back to the definition of our Laplace transform of the sine of at, this is what we have. Alright, so now this one too is the Laplace transform of the function cosine of at. So the Laplace transform of the function sine of at is equals to a over s times the Laplace transform of the function cosine of at, like this. So let me call this one equation star because we'll have to come back to this later on. So now let's go back, let's switch colors again and now go back to this one. So we are going to apply integration by parts again for this one. So we are going to have the Laplace transform of the sine of at, and this is equal to a over s multiplied by the integral from 0 to infinity of e raised to the power negative st times the cosine of at and then dt. Cool. So now let's apply integration by parts again for this one. Right, so let's do it again for the second time. D for differentiation and I for integration. I am going to differentiate the cosine of at. This is plus, next one is minus, and I'm going to integrate e raised to the power negative st. Integrating this is negative 1 over s e raised to the power negative st. Differentiating this one is negative a times the sine of at, like this. Diagonal terms, you are done with the integration, but when we multiply terms horizontally, we will have to take the integral. So the Laplace transform of the function sine of at, right, this is equal to a over s, and now let's apply the integration by parts. So integration by parts, that is going to be negative cosine of at multiplied by e raised to the power negative st. This one is divided by s. You are done, you take the limits of integration from 0 to infinity. And now negative, negative again. So there are three negative now. Negative, negative, negative. When we multiply them, that becomes negative. Then we are going to have the integral from 0 to infinity. Multiplying them horizontally, that is going to be a over s here. And now we are going to have e raised to the power negative st, and this is multiplied by the sine of at and then dt. Alright, like this. Cool. So the Laplace transform of the function sine of at, this is equal to, now applying the limits again, this one is going to 0, right? So this one is going to 0 as t is approaching infinity and everything goes to 0, and this one will go to, so for the upper limit it will go to 0, but for the lower limit, let's evaluate the lower limit and see what that is. So we have a over s. So the upper limit is going to be 0, right? So the upper limit is going to be 0 minus the lower limit. The lower limit is going to be cosine of 0. When we have the cosine of 0 is equals to 1, right? So we are going to have negative like 1 here, and then e raised to the power 0 here is equal to 1. So this one is multiplied by 1 all over s, like this. So this is what we have for the lower limit. So the lower limit is not actually going to evaluate to 0 here. And now we are now going to have negative a over s outside, the integral from 0 to infinity of e raised to the power negative st, and then sine of at and then dt. Cool. Okay, so the Laplace transform of the function sine of at, this is equal to, now what do we have here? So we have a over s, and now what is inside the bracket is going to be positive 1 over s here, because negative, negative, that becomes positive, minus a over s, the integral from 0 to infinity of e raised to the power negative st, and then sine of at and then dt. Cool. So here, this one too is like the Laplace transform of the function sine of at. So this is the Laplace transform. So let's just replace that with the Laplace transform of the sine of at. So the Laplace transform of the sine of at is equal to, now we can multiply through, we are going to have a over s squared, right, minus a squared over s squared, and this one is the Laplace transform of the function sine of at. So this one is the Laplace transform of sine of at, Laplace transform of the sine of at. So Laplace transform of the sine of at. So this is what we have. Okay, so now we want to find the Laplace transform of the sine of at, so we can just add this one to both sides. So when we do that, we are going to have the Laplace transform of the sine of at. This is added to a squared over s squared, and then the Laplace transform of the sine of at, like this, and this is equal to a over s squared. Alright, cool. So we can factorize the Laplace transform of the sine of at out. Laplace transform of the sine of at, and what is left here is 1 plus a squared over s squared, and this is equal to a over s squared. Cool. So the Laplace transform of the sine of at, which we are seeking to find, is multiplied by s squared plus a squared all over s squared, and this is equal to a over s squared. We want to isolate this, so we can multiply both sides by the reciprocal of this. So when we do that, we will have the Laplace transform of the sine of at, and this is going to be equal to, multiplying by the reciprocal of this on both sides, that is going to be s squared all over s squared plus a squared, and this is multiplied by a over s squared. Alright, cool. So there's going to be a beautiful cancellation here. This one is going to cancel this one out beautifully, and what is left is this. So that means that the Laplace transform of what we are seeking to find, which is the sine of at, this is equal to a all over s squared plus a squared. So this one is the Laplace transform of the function sine of at. Alright, so now how do you find the Laplace transform of the cosine of at? Remember, I wrote this and named it equation star. That is this one. We are going back to equation star to help us find the Laplace transform of the cosine of at. You don't have to do this all over for cosine of at. We just have to come back to equation star, and then we solve it. So equation star, let me remind you, the Laplace transform of the function sine of at is going to be equal to a over s times the Laplace transform of cosine of at. So let's recall the Laplace transform of the sine of at. This is equal to a over s multiplied by the Laplace transform of the cosine of at. This is from equation star. Now we know the Laplace transform of the sine of at is this. So what we have to do is to just replace this one with a all over s squared plus a squared. And when we do that, that is going to be equal to a over s multiplied by the Laplace transform of the cosine of at, like this. So if we want to isolate the Laplace transform of the cosine of at, we multiply both sides by the reciprocal of this. So the Laplace transform, ladies and gentlemen, of the cosine of at is going to be s over a multiplied by a all over s squared plus a squared. And there's going to be a beautiful cancellation here. This one is going to cancel this one out nicely, and what you are left is equal to s all over s squared plus a squared. So the Laplace transform of the function cosine of at is equal to s divided by s squared plus a squared. This is what we have for the Laplace transform of the cosine of at. So they look similar, they have the same denominator, but the sine of AT has A as the numerator and the cosine of AT has S on the numerator. So let's go back to our table and then fill it out and then work a few examples. So this one, the sine of AT is A divided by S squared plus A squared, and the cosine of AT is S divided by S squared plus A squared. So these are the Laplace transforms for the functions sine of AT and cosine of AT. So this is what we have. So now if I are given an example, let's do a very simple exercise here real quick, right? So if we are looking to find a Laplace transform of, let's say, sine of 3t, this is going to be equal to the Laplace transform of the sine of AT is A over S squared plus A squared. So A here is equal to 3, right? So that is going to be 3 all over S squared plus 3 squared, and that is equal to 3 all over S squared plus 3 squared is 9. So 3 over S squared plus 9 is the Laplace transform of the function sine of 3t. So if you want to find a Laplace transform of, let's say, cosine of 4t, right, this is equal to the Laplace transform of the cosine of AT is S all over S squared plus A squared. So here that is going to be equal to S divided by S squared plus, here A here is equal to 4. So that is going to be 4 squared. And this is equal to S divided by S squared plus 4 squared is 16. So S over S squared plus 16 is the Laplace transform of the function cosine of 4t. So these are the Laplace transforms of these trig functions. So in my next video, I am going to find the Laplace transform of the sine hyperbolic and the cosine hyperbolic of AT. So join me in my next video as we derive the formulas of the Laplace transform of these hyperbolic functions. And if you find this video helpful, give me a thumbs up and subscribe to Calculus Diaries, and I'll see you in the next one. Bye bye.